everybody. So this is about mass moment of inertia for slender bars, and you should definitely watch the other video introducing this first, which goes over how you integrate to solve for the mass moment of inertia. But that's not how you would do it in practice. In practice, you would use the parallel axis theorem, which you've seen before when we're doing centroids and area moments of inertia. But now, this is specifically for the mass moment of inertia. So let's start with maybe a simple example. So let's say you already know that for this slender bar of mass m and length L, the mass moment of inertia here about the center of mass is known, 1/12 ml squared. Like you got that from integrating. But then let's say we have other points. Let's just make up some values over here. So, okay. So what's the moment of inertia about point B? Is it more or less than C? So we already know that the moment of inertia about the center of mass is a minimum. It doesn't get any less than that. So if we move anywhere else, like over here, it's more. If we move over here, more. Over here, more. So definitely this is more. So it's this plus something extra. Okay, how much extra? The mass of the object, in this case the entire bar, times the distance between these two parallel axes squared. So that distance between points C and D squared. So say we use this as an example. So that's 1/12 ml squared plus the mass of the whole bar times the distance between here and here, L over 4 squared. So that's the answer. So that's 1/16 and 1/12 is, let's see, so 4 over 48, 3 over 48, so 7 over 48 ml squared. So see, this is bigger than this. Okay, let's say, what's the moment of inertia about A? Again, definitely more than this. So it's this one plus extra. How much extra? The mass of the bar times the distance between these two parallel axes, between A and C, squared. So here it would be 1/12 ml squared plus mass of the bar. The distance between these two would be L over 2. Okay, so 1/12 plus 1/4 is 4 over 12, so 1/3. Okay, so that's how you use the parallel axis theorem. Warning, the parallel axis theorem is always moving with respect to an axis going through the center of mass. So that is important. Here, here, here. Not between, like, say, A and B. Neither of those is going through the centroid. So you wouldn't use the parallel axis theorem to go between A and B. So let me just show an example of what not to do. So you would not, let's say okay, so between A and B, which is more? This one is more because it's farther away from the center of mass. So this one is more, this one is less, this one is a minimum. So it's like plus extra, and this is not correct. I'll just say before I even continue. This is not correct. It's not like you go from B to A, the mass and then the distance between A and B. So that would be like 7/48 ml squared plus the mass, and then the distance between these two is L/4, and then you square it. So this is not right. This is not the way to do it. You always go from the center of mass to somewhere else. Okay, let me just make up some example. Let's say we have some shape, and then we have, let's say, points A and B and C. And let's say point C is the center of mass. And then let's say you do some measurements and you solve, like these are all 2 meters apart. And based on some data you collected, the moment of inertia about point B for this object is 100. Okay, what's the moment of inertia about A? How do you get it? You wouldn't just use the parallel axis theorem between A and B, because neither is an axis going through the center of mass. You could go from B to C, which is the center of mass. Which is more between B and C? This is more, right? Because through the center of mass is a minimum, which means we'd have to subtract some amount. Right? Again, because this is more and this is less. How much are we subtracting? The mass of the entire thing, which I should make up some number. Let's say it's 10 kilograms. Times the distance between these two axes. So the distance between B and C. Okay, so like if we just use these numbers, 100 minus 10 kilograms times 2 meters squared. Okay, so that's 40, so then 60. And then from here, now we can go from C to A. So about A is, again, which of these is more? A is more. So plus some amount, the mass, times the distance between these two, 4 squared. Well, let me just write it symbolically. The distance between A and C squared. So in this example, 60 plus 10 kilograms, 4 meters squared. Okay, right, and then solve that. Okay. Now let's do that example from the other video with that L-shaped bar, which I was mentioning. You can integrate. In theory, that's how I kind of explain the concept, but that's not really how you would solve it practically. So let's say, let me just make up some values. Let's say this is L1, and I'll make a number, 6 meters. This is L2, 4 meters. And let's say the entire L-shaped bar is 20 kilograms. Okay, what's the moment of inertia about right here? The z-axis. So rather than integrating, we already know that the moment of inertia about a slender bar through its own center of mass, I'll jot it down over here, 1/12 ml squared, through its own center of mass. And this L-shaped bar looks like a composite of a horizontal bar and a vertical bar. So for the horizontal bar by itself, it's like this center of mass, 1/12 ml squared. But what m and what l? The mass of only this horizontal bar. The length of only the horizontal bar. But what is the mass of only the horizontal part of the bar? So we know that the entire bar is 20 kilograms, and the entire length of the bar is L1 plus L2. So the density is 20 kilograms. The density is 20 kilograms over the total length of the bar, 10. So it's 2 kilograms per meter, the linear density. So for every meter, 2 kilograms. So that means this horizontal bar is 12 kilograms. This vertical part of it, 8 kilograms. Okay, so we know that this is 12 and this is 6 meters. But this is the moment of inertia about here. We need it here. So we have to add extra, plus extra. How much extra? The mass of this bar times the distance between these two parallel axes. So in this example, L1 over 2 squared. Okay, so this is for the horizontal part. Now the vertical part. So for the vertical part, this is the center of mass, halfway up. So for this bar about its own center of mass, 1/12 ml squared, where the mass we're talking about here is 8 kilograms. The length here is 4 meters. But we're not rotating about here. We need it to be here. So we have to add extra. How much extra? The mass of that bar, 8 kilograms, times the distance between these two parallel axes squared. So how far is this? Just look at this triangle. We look at this triangle. 6 over here, halfway up, 2 over here. Right? So square root of 6 squared plus 2 squared. And then see how there's like the square root and the square. I'll just leave it like that. Okay, and that's how you would solve the moment of inertia of a bar like this using parallel axis theorem. I wouldn't recommend doing the integral way. Doesn't this way seem much faster and easier and less prone to making mistakes? Okay, so practice this way, this using the parallel axis theorem. And then let me know if you have questions. Then I'll see you on the next video.